B bar is equal to del bar cross line integral mu naught I times dl dash vector upon 4 pi r. We know that B bar is equal to del bar cross A bar from the definition of vector magnetic potential. By equating these two expressions, we can say that the magnetic vector potential is equal to line integral of mu naught times I dl dash vector upon 4 pi r. Is it clear? Then this is the expression of magnetic vector potential for a long current carrying conductor or for a line current distribution. Is it clear? Now we can see the relationship between vector magnetic potential and the magnetic flux. Since the magnetic flux is equal to open surface integral of B bar dot ds bar, then in the place of B bar we are going to represent the curl of magnetic vector potential. Now by applying the Stokes theorem to that, then the closed line integral A bar dot dl bar, it becomes. Then from this expression we can say that the magnetic flux can be the closed line integral of the magnetic vector potential. Okay, the units of the magnetic flux is Webers. Are you clear, all of you? Then this is nothing but the magnetic scalar and vector potential. Remember, this expression is very important. This is a magnetic vector potential expression for a long current carrying conductor or for a line current distribution. Is it okay? Yeah, this is the topic of magnetic scalar and vector potential. Is it okay? In the next we are going to see the topic of forces due to magnetic fields. Is it clear? Now coming back to the forces due to magnetic field, we know that the force and the direction of magnetic field and the current, all three are the mutually perpendicular to each other. That means we can able to say that the direction of force is equal to the cross product of the direction of current and the magnetic field produced by that. Is it clear? Now we are going to observe that forces due to magnetic fields. There are three ways in which forces due to magnetic fields can be experienced. The first one is force on a charged particle, whether it may be a stationary charge or a moving charge. We are going to see the combination of these two in the static and magnetic fields. Now forces on a current element, it may be a differential current element. Now force between two current elements. Is it clear? Now observe that force on a charged particle. In electrostatics, according to Coulomb's law, electric force on a stationary electric charge is given as F vector is equal to Q times the electric field intensity. The units are newtons. Now we are going to discuss about here. Observe very carefully. Here Q is a charge, that means it is a source in electrostatics, but a magnetic field can exert force only on a moving charge. The magnetic force experienced by a charge moving with a velocity u bar in a magnetic field is, since here in electrostatic the source is a stationary charge, here in magnetostatics the source is a charge moving with some velocity. Here I am going to assume that the velocity is u bar. Now u bar is a vector quantity and B is a vector quantity. I am going to consider the cross product of these two. Therefore we know that the cross product of this is going to be the force direction. Is it clear? Therefore the magnetic force is equal to Q times its velocity cross B bar newtons. Therefore the total force on a charged particle in the presence of both electric and magnetic field is the combination of electric force and magnetic force, which is Q times electric field plus Q times the velocity cross B bar. If you take Q as a common term, then you are going to observe this expression. Remember, this is known as Lorentz force equation. Very important for 2 marks question, Lorentz force equation. They will simply say that write the Lorentz force equation, then you have to write that. This is the topic of force on a charged particle. Okay, now we are going to see the force on a current element. Now observe that here from this expression. Now let us consider a current carrying conductor Now I am going to talk about the current element. Why? Because the topic is force on a current element. I am going to talk about this current element. This current carrying conductor produces a magnetic field. Now the force on this current element is going to be, observe that just now we have seen that the magnetic force is equal to q times the velocity cross b bar, where q times the velocity is a charge q moving with velocity. Consider a current carrying conductor of length L as shown in below. The force on a current element, okay, IDL of a current carrying conductor due to magnetic field, here IDL, okay, due to magnetic field B bar is, observe that here we are going to talk about a small length, therefore the force is also going to be a small, then it is a source here. Observe this expression, the source is here q times the velocity. Now here the source is IDL cross B bar, that's it. This is the force on a differential current element or a simply current element. Okay, now we are going to take the overall force is nothing but the closed line integral of IDL vector cross B vector newtons, similar for surface current, volume current. Now we are going to see last topic, force between two current elements. Is it clear? Now let us observe that this is one coil, this is another coil, or a loop, current loop, this is another current loop. Now see, the direction of current is like this, since the direction of current is always from positive to negative, and the direction of current here is like this. Are you clear, all of you? Now if you observe that very clearly, this is current loop 1, this is current loop 2, this is the current element I have considered. Since the current is I1 for this current loop 1, the current element becomes I1 dl1 vector. This is the current element 2, I2 dl2 vector. Now I am going to talk about here the force is due to this, the force is df1, here the force due to this is df2 vector. Now I am going to see these arrows very carefully. This arrow represents the force on this current element due to this current element. Now this arrow represents the force on this current element due to this current element. See the representation, R21, R12. R21 is nothing but force on this current element due to this current element distance. Then R12 represents force on this current element due to this current element distance. Is it clear? Now I am going to determine the force on the current element I1 dl1 vector due to the field B2 field produced by this current element. Okay, that's why observe that I'm going to talk about here. Actually the force is df1, due to this current element it again becomes d of df1. Is it clear? This is very important, carefully observe that. Now observe here, consider the two conductors in parallel as shown. Okay, this is the figure. According to Biot-Savart's law, both current elements produce magnetic field. Is it clear? We know that according to Biot-Savart's law, both the current elements produce magnetic fields. The force d of df1 vector on element I1 dl1 due to the field db2 produced by element as shown in figure is, that means it is the force on the loop 1. Okay, it is the force on loop 1, that means on this current element due to the field. Here I am going to talk about differential, that's why the field also differential, produced by whom? The current element 2. Now we are going to write from this expression, I dl cross b bar. Similarly I am going to write d of df1 is equal to I1 dl1 cross db2. That means it is the force on the current element 1 due to this current, due to this magnetic field. Is it clear? Now according to Biot-Savart's law, we know that db2 can be written as mu naught times I2 dl2 vector cross. Here I am going to take unit vector R21. Why? Because it is the distance from coil 2 to coil 1. Is it clear? Divided by 4 pi R21 square. Now this expression I am going to substitute here like this. Then I1 I2 mu naught by 4 pi is going to be constant. Now I am going to write dl1 vector cross dl2 vector cross r21 vector divided by r21 whole square. Now I am going to separate these two differential, therefore it becomes two line integrals. Is it clear? Then finally I am going to say that this is the expression for force on a two current loops in a parallel condition. That means force between two current elements. Is it clear? This is the expression, very important. Is it clear, all of you? This is forces due to current elements. Is it okay?